So in order to, the kind of heuristic approach to deriving the best fit model from a noisy data set is what's called validation. And in order to do this, we actually have to break our data that we have into two sets. We have a training set, just like before, which we used to train the model. And we have a separate piece, collection of data, which we don't touch. We don't use it to train on, so the model is blind to this data. And we then apply it later to measure how well the model performs. We never measure performance based on the training data. It's already tainted, right? So we always use a separate piece of data to measure performance. So this is what I've done in this case. I basically took the same kind of data, and I broke it up into two groups. So you can see here the setup in Python. I just basically sampled 10 random points out of 20, and I put them in the training set, and I put the other 10 points in the validation set. And this is a very typical setup. You have two sets of data. And what we're going to do is we're going to train the same systems on the training set. We're going to train a few of them. And then to measure their prediction capacity or their performance, we're going to apply those models to the validation set and measure the error based on that. Okay? So now we're going to have two sets of error curves. We're going to have the training error, which as the model complexity grows, the error will always go down, right? A more complex model will always model the training data better, always, right? But we have this other curve, which was going to be the mean square error on the validation set. And ideally, that curve will get lower and lower as the model is fitting more and more of the system of the data. Once the model starts to model the noise of the training set, the error in the validation will actually go back up. It'll get worse, right? This is known as the point of overfitting, which is another common term in machine learning, but it's actually very intuitive. You overfit the data when you start to model the noise. Okay, so here is that setup. We have 11 trials, and each trial would just increase the degree by 1. So we go from a straight line, this is 0, all the way up to an 11th order polynomial. You can see all the fits here. Some of them get really crazy, but the blue ones are the ones we're training on, right? So by the end, they fit the blue points exactly, but the red ones are the ones we're actually measuring performance on. And here's the two curves. The blue curve is the error in the training set, and by the end, it starts to approach 0, right? And the red curve is the one we actually care about. This is the performance on the validation set. And this is the heuristic. This is the best practice approach for picking the right model. You say the best model is the one that has the least error in the validation set, right? It's just one approach, but it's a very common approach that we're going to use in this class. Of course, it depends on how you split up your sets, what proportion of your data goes to training versus validation, how you randomize those. It all becomes just best practices, okay? It's just through practice. There's no set rules for this. This is a very simple example that I've just done for demonstration. And now we pick the lowest point. Sure enough, it's degree 3. And here's the dark line. This is, based on this approach, the best fit. It's a cubic, right? You see here how we're training the model, right? We train it, fit is the training function, on the training data, both for the X features and the Y results. And then we apply that model. This is predict function. So of that model we use to predict, based on the X train, we get the Y train prediction, Y training set prediction. That's the blue line. It's going to get better and better. And then we also apply the model to all the validation data. We get validation predictions, and then here we just plot, or we measure the mean square error, right, of the training prediction and the validation predictions. That's as far as of a fundamental technique or heuristics that we're going to use in this class. Okay, so if you understand this, then that's all you need to know. So obviously a lot of complexities in this, but that's the basic idea. One, we have infinite complexity to model complex data sets, but we want to restrain that complexity to make sure that we don't model the noise. we derive the model that represents the system in the best general way. Okay, so here is our supervised learning model, and we just build in a validation. And this is how this works, right? Here we have the same exact model, but before we make a decision about our model, we actually have this separate piece of validation. So what we do is we take some percentage of training data. This is also heuristics. 70 is something I use. You can use 60, 50, whatever. We take some proportion of the data as training data. We learn a few models, right? We vary the parameters of the model, the complexity, whatever, to make a series of potential models. And we have a separate set in reserve, which we then use to validate the models to actually derive the best one.